This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
The law of inertia says that an object will continue to move with a constant speed in a straight line, unless it's acted upon by an outside agent. Hidden within this law is the consequence that all motion is relative. Whether a body is in motion or at rest depends on the point of view of the observer. Two very important men were born in 1564. William Shakespeare in Stratford and Galileo Galilei in Pisa. One became a bard who set the world spinning with his poetry and plays. The other became the father of modern science, who showed how the earth could be spinning. As a youth in Pisa, Galileo had first set out to study medicine, but abandoned medicine for mathematics. In 1589, he was appointed professor of mathematics at the University of Pisa. 3 years later, he accepted a position at the University of Padua, where he lectured in Euclidean geometry, Ptolemaic astronomy, and Aristotelian mechanics. In Padua, he conducted his noted research on falling bodies and inclined planes. In the year 1610, a Dutch lens grinder named Hans Lippershey had discovered a remarkable new device, the telescope. As soon as Galileo heard about it, he figured out how it must work, came up with his own design, and built a telescope of his own that magnified images by about 9 times. Galileo didn't claim that he invented the telescope, but he also didn't bother to point out that he hadn't. He built a number of larger, more powerful telescopes, including one that would magnify images about 30 times. Today, 2 of them are on display in the Museum of the History of Science in Florence. With these telescopes, Galileo looked at the sky and made some remarkable discoveries. The moons of Jupiter, which even today are called the Galilean satellites. Mountains on the moon. The phases of Venus. And spots on the face of the sun. Even now that we've walked on the surface of the moon, Galileo's sketches reveal that his views were amazingly accurate. In time, Galileo's astronomical discoveries, along with the ideas of Copernicus, would intellectually shatter the serenity of the heavens. To anyone who dared to look through Galileo's telescope, what they saw was the beginning of the end for the worldviews of Aristotle and Ptolemy, and the beginning of a great deal of trouble for Galileo Galilei. By the early 17th century, Europe had seen the Renaissance, the Protestant Reformation, and the Catholic Counter-Reformation. Sweeping changes had shaken every part of the medieval system: religion, art, literature, music, mathematics, and the sciences, especially astronomy. Before the Renaissance, Aristotelian mechanics and Ptolemy's design of the heavenly spheres were the order of the day. They were the logical, accepted, and unchallenged natural order of the universe. And so it was, until a Polish monk looked upward and saw things differently. In opposition to the Ptolemaic view, Copernicus saw the Earth as just another planet circling the larger, grander sun. Copernicus, like Martin Luther, challenged the Church's interpretation of Holy Scripture. But the Copernican system also seemed to defy elementary common sense. Heavy objects naturally fell toward the center of the Earth, because that was the center of the universe. If the Earth really is spinning and hurtling through space, why doesn't everything fly off? And if the Earth really is spinning, why should an object dropped from a tower land directly below? Why doesn't it land in the next city-state, or at least some distance away? 300 years ago, those were logical, intelligent questions, and Galileo Galilei set out to find the answers. Galileo was, despite his independent nature, a very popular figure, generally respected and admired. And to the Church, his God-given intelligence made him a favorite son. No doubt, Galileo enjoyed the attention. His hunger for fame was enormous, but his thirst for knowledge and for truth was even greater. His first book, The Starry Messenger, revealed his remarkable observations. The publication of The Starry Messenger elevated Galileo to a position of renown throughout Europe. Yet in certain circles, his discoveries were not altogether welcome. Through his telescope, Galileo had seen something unimagined, or at least unspoken, by the followers of Ptolemy. The moons of Jupiter seemed to prove that the Earth wasn't the center of all motion in the heavens. Did he have within his sights the proof that Copernicus had been correct? Contrary to both Aristotle and the doctrine of the Church, was the Earth merely another planet orbiting around the sun? If that were true, the question remained, why in the world doesn't everything spin off? Aristotle's ancient view was that all things, by their nature, have rightful homes to which they want to return. His ideas of absolute rest and absolute motion seemed confirmed by common sense. And based on the common experiences of everyday life, how could anyone take the idea of the Earth's hurtling through space seriously? It was one thing for Galileo to criticize the prevailing Aristotelian point of view, but quite another to show how and why things worked within the Copernican system of planetary motion. But even before the invention of the telescope, Galileo had prepared himself to do exactly that. To lay the groundwork for his law of falling bodies, he had painstakingly observed and timed balls rolling along inclined planes. These experiments also led him to another profound idea that would come to be known as the Law of Inertia. Galileo realized that a ball, after rolling down one inclined plane, would roll up another until it regained its original height, no matter what the steepness of the second plane was. If the incline of the second plane was shallower, the ball would roll farther along, not stopping until it was as far above the horizontal as it had been at the start. The more nearly the second plane was horizontal, the farther the ball would roll, trying to regain its original height. Therefore, on a perfectly horizontal plane with a smooth surface, a ball would never come to rest. It would keep rolling forever. This was the crucial realization that Galileo needed to explain why everything, including his critics, could keep up with the spinning surface of the Earth. A body in horizontal motion tends to keep moving that way forever. But everything on the surface of the Earth is in horizontal motion at exactly the same speed as the surface of the Earth itself. There's not even any friction to affect a body's motion because everything moves together. With this remarkable concept, Galileo overturned the ancient Aristotelian dogma that it's natural for all bodies to come to rest. Although Galileo's concept was brilliant, it wasn't entirely accurate. Still influenced by the Platonic ideal of circular motion, Galileo thought that a body in motion would continue forever, but only in the horizontal direction, not in a straight line, but round and round, following the surface of the Earth. A generation later, René Descartes straightened everything out, giving the law of inertia its final shape. Objects in motion don't tend by themselves to come to rest. They tend to continue as they are until something interferes. That fact's easier to see now than it was in Galileo's day. Today, few would disagree that the planet Earth hurtles around the sun. A sun that moves around one corner of a galaxy that moves alone in a cluster of galaxies, all streaking through the unimaginable vastness of the universe. How does the idea of rest fit into this grand scheme of things? It doesn't. Nothing in the universe comes to rest. Instead, anything and everything will continue to move as it is, in a straight line at a constant speed until something interferes with it. That's the principle of inertia. And it's both as simple and profound as any idea that's ever been pondered. Obviously, objects can seem to be at rest, but that's only because they're in the same state of motion as the viewer. Whether an object is at rest or in motion depends completely on viewpoint and whether the observer's moving right along at the same speed. Absolute rest does not exist. Absolute motion does not exist. Even hurtling through space at an incredible speed, relative to the moon or the sun or the center of the galaxy, the natural tendency of any object is to retain whatever motion it has. In Galileo's day, that was a very difficult concept to accept. To an Aristotelian, the motion of a cart required and had a logical explanation. Unless something came along to push or pull it, it wouldn't move. Therefore, its natural state was that of rest. But to the modern observer, a vehicle in motion needs no explanation. This coasting object will keep moving until the brakes or something else brings it to a state of rest. But what about an object that's not just moving horizontally along with the surface of the Earth? What about a projectile launched into the air, or a ball dropped from a tower? Shouldn't the spinning Earth leave the falling ball behind? Galileo said it shouldn't. He said the ball should continue to move horizontally with the Earth, even as it falls vertically toward its surface. In the Renaissance, this concept was as hard to grasp as quicksilver. So, Galileo offered his contemporaries an analogy. He asked people to picture a ball falling from the mast of a moving ship. To a sailor on the deck, the mast is standing still. He wouldn't be surprised to see the ball fall straight down onto the deck at the foot of the mast. But anyone on shore would see the ship and, of course, the mast in motion. An Aristotelian observer would have no doubt at all about what should happen. The ball should fall directly toward the center of the earth while the ship sails out from under it. That sailor on deck would see the ball hurtle toward the rear of the ship rather than fall to the foot of the mast. Though the experiment was probably never performed during Galileo's life, the results are precisely what he predicted. The ball falls straight down along the mast. The ball falls along the mast because both objects, ball and sailboat, share the same initial motion. If they don't share the same initial motion, then the result is just as the Aristotelians would have expected. But when dropped from the moving mast, the ball falls vertically while moving horizontally with the boat. Together, these motions form a curved path, a parabola. Galileo realized that these same principles would cause the motion of any projectile to follow a parabolic curve, whether at sea or on land. A ball dropped anywhere on the surface of the spinning earth behaves the same. Here, sharing the horizontal motion of the planet, it falls straight downward and lands at the base of the tower. In these terms, Galileo saw and proved something new under the sun. In 1616, Galileo was summoned to Rome. He was told to neither hold nor defend this idea of the earth moving around a stationary sun. Galileo was put on trial in 1634. His fame and prestige made it unthinkable to go further than the mere threat of torture. But to Galileo, who knew very well how machines worked, that was enough. He publicly recanted the Copernican system of planetary motion. Ironically, in the future, no serious scientist would deny Galileo's evidence. The principle of inertia, conceived by Galileo and refined by Descartes, became Isaac Newton's first law of mechanics. Found guilty in spite of his famous retraction, Galileo spent the remaining 8 years of his life under house arrest at his estate in Florence. According to legend, as Galileo headed into the exile of house arrest, he said, "Eppure si muove." Nonetheless, the earth moves. The principle of inertia states that an object will continue to move in a straight line at a constant speed unless acted upon by an outside agent. The only meaningful description of motion is relative motion, motion of one object with respect to another, which is used as a frame of reference.
This material is based upon work supported by the National Science Foundation under grant number SPE 8318420. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.